so we don't have to run this?
Um,
If there's room,
yeah, if there's room, I mean,
I'll save you the trouble. I just walked right in here, I didn't actually check, so. Okay. Go take a peek.
might actually be room in the other room, I'm not sure. Probably not now, but.
We're not going in this one?
There's
Oh,
two seats.
there's two seats, okay,
That I think I saw. So.
okay. Well, we're still gonna have one person here, so it's whatever you guys wanna do. We're doing a fun demo today, and so I get to do that in here too for you guys, so.
There's how many in there? Oh,
3, oh, good.
We'll leave them there.
sorry, I miscounted them.
Well, we can't be having that. You know, show up and then- Way up there. Or maybe it's the setting. It doesn't like explore it. You can stop it when I started if you want, or whatever. I'm gonna go. And then he wants to do the rocket first off, so I'll show you how much I'll call that. So I'll go ahead with it. Right.
Okay, okay, let's see. You can check that camera. Okay, let's first see what that we're going. So it's just an invitation of, in a sense, the third law of classical mechanics, Newton's third law, and also Newton's third law is equivalent to conservation of linear momentum. We're going to talk about conservation of linear momentum in about 2 weeks. So they are practically the same statements, at least in the context of classical mechanics. So what happens here is that you have some flammable vapor inside the bottle. And when you ignite it, the gas inside the bottle expands and leaves the bottle from the opening. And of course, this generates a recoil force, and the bottle is wide. Can you do it once more? Or? Let's do it again.
You need to flush it out.
Yes. So they're cleaning the bottle from the exhaust that is left over, and now filling again with alcohol. Is it ethanol? Methanol?
Isopropyl, or no, ethanol. It's 85% ethanol. Does it matter how much is put in there?
It probably does. You don't want too much because it's going to spill before actually it's going to ignite like it ignited before outside.
So what I'm doing right now is I'm coating the inside surface of the bottle so I get more surface area so it vaporizes faster.
So we don't want this bottle to catch fire, right? Well, okay, let's do another. Thank you. So, okay, so I see some questions on the board. Are those homework questions? Homework? Okay, we're going to deal with today. I just have to say a few more words about some particular forces that we're going to encounter this semester. So we've already talked about the gravitational force, the weight of an object. The other forces that we encounter every day are the normal force. So this is the force that cancels out the gravity. So the force that acts on this remote control is the gravitational force directed downward, but you see that the remote control doesn't accelerate in downward direction. The reason for that is that there is another force that acts in opposite direction and cancels out exactly the gravitational force. So the net force acting on this remote control is zero, and that remote control doesn't accelerate, doesn't move at all. So when you have a contact between two objects, like this remote control and the surface of the table, there are always two contact forces that appear. One of them is the normal force, perpendicular to the surface of the contact. The other force that also appears is the friction force. It is again a contact force, but unlike the normal force, it is parallel to the surface. And actually, the friction force is, in a sense, a smart force because it senses the direction on which some external force is applied, and it acts in opposite direction, but still parallel to the surface of the contact. So both the normal force and the friction forces are electromagnetic in origin. So they appear because of the electromagnetic interactions between the molecules of the remote control and the table. Well, we distinguish two distinct types of friction forces. The first type of friction force we call static friction force, and it appears when there is no relative motion between the two objects that are in contact. So for example, right now, no motion, relative motion between the remote control and the table, and if I apply a little bit of force, this remote control doesn't move at all, doesn't accelerate at all, because the friction force, static friction force, cancels out the force that I'm applying. So it senses the magnitude of the force that I'm applying, it senses the direction of the force that I'm applying, and it generates a static friction force in opposite direction. Well, there is a maximum value that the static friction force can have. And experimentally, you can show experimentally that the maximum value of the static friction force is equal to a coefficient of friction, so dimensionless number mu s times the magnitude of the normal force. So this is experimental fact. It is practically, it's very difficult to prove theoretically, but it works. So when the external force exceeds this value, this maximum value of the static friction force, the object starts to move. And in state of static friction force, you have another force, kinetic friction force, that is generated. Now, okay, so here it is. I am applying force to this laptop, and it doesn't move. If I push a little bit harder, eventually it starts sliding. At the moment when it starts sliding, instead of static friction force, we see kinetic friction force. And experimentally, the kinetic friction force has magnitude given by another coefficient of friction, mu k, coefficient of kinetic friction, multiplied by the normal force. Okay. So in general, the coefficient of kinetic friction is usually smaller than the coefficient of static friction. In general, any coefficient of friction depends upon the nature of the materials that are in contact. So for example, the coefficient of friction between this laptop and the table is some number. While if instead of a table I had an icy surface, that coefficient of friction, of course, would be some smaller number. And it will be easier to move, to accelerate, to overcome the friction force. So since the coefficient of static friction is larger and coefficient of kinetic friction is smaller, once the object starts moving, it is easier to keep it moving. It is more difficult to get it started, but once it starts, it moves. Easier. The reason for that, coefficient of kinetic friction is smaller, and therefore the kinetic friction is smaller force than the static friction. Another unexpected fact is that the coefficient of friction, so we're talking about friction between smooth surfaces, right? Smooth surface here, smooth surface here. So unexpected fact, experimental fact, is that the coefficient of friction doesn't depend upon how much surface is in contact. So the coefficient of friction between this object and the table and the friction force is the same no matter if this object is this way or if it is this way or any other way. The area of contact doesn't matter. And you see it from the formulas. The only thing that matters is the normal force, which for horizontal surface is usually equal to the weight, to the gravitational force acting on the object. Okay, so well, this pretty much covers the basic forces that we're going to encounter. We can talk a little bit about tension force when you have objects connected with cables, with strings. But it is easier to see tension forces when we solve a problem that includes some string, cable, pulleys, and other devices. Okay, so knowing this, let's see questions, remarks, comments from here, from online people. Okay, if not, let's look at the homework problems that are on the board. Maybe let's start with question number 2. It is a conceptual question, I guess. Let's see what that question is. Let's see that. Okay, so here. So in question, it is a conceptual question, and I guess that well, let's see what the question is. So you have several statements, and they're asking which of those statements is correct. So the first statement is that SUV hits a stationary motorcycle. Since it is stationary, the motorcycle sustains a force, a larger force, I guess, right? A greater force than the SUV does. Well, this statement is clearly wrong because Newton's third law says that action and reaction forces are equal to each other in magnitude. So both the motorcycle and the SUV are subject to the same force during the collision. Well, of course, the motorcycle has a smaller mass than the SUV, and the effect of that force will be more significant on the motorcycle. But this is a separate issue. The action and reaction forces must be equal to each other, and therefore this statement is not accurate. The second statement, a semi-truck crashes all the way through a wall. Since the wall sustains a greater force than the truck does. Again, the same reasoning. Action and reactions should be equal to each other, and which object sustains more damage doesn't matter. it depends upon the nature of the object, the wall, the truck, or whatever object it was. The third statement, Sam and his sister do ice skating. They push off against each other and fly apart. Sam flies off with greater acceleration. Well, this is marked as wrong, and it is wrong. Because, look, they don't say it explicitly, but usually 18 years old person is more massive than a 9-year-old. So during this, their interaction, you have action-reaction force equal in magnitude, acting on the 9-year-old and the 18-year-old. The same force in magnitude acts on each of them. However, since the 18-year-old is more massive object, that same force generates smaller acceleration, because Newton's second law says, right? If you write Newton's second law only for magnitudes, if you have that acceleration is equal to the force, the net force, divided by the mass of the object. So the second, the 18-year-old has larger mass, and as a result, his acceleration is small. The force, the net force acting on the 18 years old and the 9-year-old is the same in magnitude. So this is why that statement is not accurate. And the last statement is about spacewalk. So two astronauts are walking, spacewalk, throwing a ball back and forth between each other. In this game of catch, the distance between them remains constant. Well, is it? So distance between them remains constant implies that they're not moving with respect to each other. But in reality, this is not going to happen because of exactly an effect similar to this bottle that flew. Exactly the same effect. So imagine that when the first astronaut throws the ball, well, he acts on the ball with a force. The ball is going to act on him. And as a result, he's going to feel a force in backward direction, the action force in backward direction, and he's going to accelerate in backward direction. Similarly, when the second person catches the ball acts on him with an action, and as a result, he's going to fly in direction of the motion of the ball. So basically, in this game of catch, the two astronauts are going to accelerate away from each other. The distance between them is going to increase. So this is why neither of the choices here is acceptable. This is a little bit, they should have, well, the third statement about the 18 years old and the 9 years old, that statement, they should have said explicitly that their masses are different. The 18 years old is more massive in order it to be more. Okay. Any remarks about? If not, let's go to next question. Is question number 11, I guess. Let's see what is question number 11 from the homework assignment. Okay, it is another multiple choice question. Let's see what it says. So you have a suitcase, 10 kilogram suitcase, on a scale that is in an elevator. The elevator is accelerating up or down when the scale reads what? So, well, we have to talk a little bit about apparent weight. So now look, this apparent weight concept is something that can generate quite confusing questions and questions that people make mistakes. In reality, the situation is not that complicated. So imagine that, well, imagine that I'm standing on an elevator somewhere on the 100th floor of the CS building in Chicago, let's say. And suddenly the cable that supports the elevator is cut. What's going to happen? Well, the elevator is going to start accelerating in downward direction with acceleration 9.8, and my body also would accelerate exactly with the same acceleration. I do not need to touch the floor of that elevator in order to fall together with it. So I'm not going to feel any normal force from this elevator. The contact between us is practically going to be negligible, and we're still going to fall down together. So I'm going to feel weightless, even though the gravitational force is acting on me and it is accelerating me with acceleration 9.8. The same gravitational force as usual is acting on me, but I just don't feel it because I don't touch the ground. So the conclusion here is that the apparent weight, the weight that a person feels, is actually the normal force with which the floor or the scale, bathroom scale, acts on my feet. This is what I feel. I do not feel directly the gravitational force. I feel my interaction with the floor or with the bathroom scale. In other words, when they ask about what is the apparent weight, what is the weight that you feel, or what is the weight that the bathroom scale is going to show, the scale is going to show the normal force. This is what it measures. And in this case, we can actually answer all questions of this type looking at the following simple setup. Here is the floor of the elevator, and here is the person standing on this floor. The forces that act on this person are his weight, the gravitational force, which is the mass times 9.8. And the other force that acts on this person is some normal force, perpendicular to the floor, sorry, in upward direction. So they say that, let's say that this elevator together with the person is, let's say it is accelerating with acceleration directed this way. So this is the direction of the acceleration vector. It doesn't mean that the elevator is moving in upward direction. The elevator may be moving in downward direction, but if it is slowing down, the acceleration is still going to be pointing up. Now, if you want to introduce some coordinate system, let's use a coordinate system that has positive y-axis in downward direction. It doesn't matter what choice you do, you make. Let's choose positive direction to be down. In this case, the net force that acts on the person is going to be the gravitational force mg in positive direction and the normal force F normal in negative direction. So this is the net force acting on the person. According to Newton's second law, that net force is equal to the mass of the person times his acceleration. Notice that in this case, I'm not using vector signs because all the vectors are in the same direction. But since the acceleration vector is pointing in negative y direction, this number is a negative number in this particular case. Just some negative number, -5, -5.7, whatever it is. Well, the apparent weight, the weight that this person is going to feel, or the weight that a bathroom scale would measure, would be the normal force. And now solve this equation for the normal force. You're going to get F normal is equal to, well, let's do it slowly. Move this mg to the other side with opposite algebraic sign. So negative Fm is left here, and you have ma minus mg multiplied by -1, and you have the normal force is equal to the mass times g minus acceleration. Okay. G is positive 9.8. The acceleration is negative 5.2 or whatever number it is. So negative times negative is going to add something to the 9.8, and therefore the apparent weight of this person is going to be larger than his real weight. In a similar manner, if the acceleration were directed downward, this would mean that in this case the acceleration as a number would be a positive number, and you would subtract something from 9.8, and the resulting normal force or the resulting apparent weight is going to be smaller than your normal weight, your gravitational force. So let's see for this question. So you have a 10 kilogram suitcase for this question. This means that the weight of this suitcase is the mass that they give you multiplied by 9.8. So it is approximately what 90.98 newtons approximately is his real weight. 998 newtons real weight. So now but now the elevator is accelerating up or down, and they say that the scale reads 75. Well, if the scale reads smaller number, this means that A here is a positive number, so you subtract 5.2 or whatever A is from 9.8, and the result is going to be a smaller than 75 number. In other words, the acceleration in that case of the elevator is directed downward. And this is the right choice. So similarly, so the justification is this reasoning. It may look quite complicated and so on, but this is the only way not to make a mistake, because those apparent weight questions could be quite confusing sometimes. So when they're asking about apparent weight, never look at the direction of motion. Only look at the direction of the acceleration. The direction of acceleration may be opposite to the direction of motion. Okay, part B. Now you read larger number than the real weight. The scale reads larger number. This means that the acceleration is a negative number. Negative times negative gives you positive, and therefore the acceleration is in upward direction. So again, those apparent weight questions could be quite tricky. So we just have to exercise, and you have to just think about the reasoning that I presented on the board. Let's see questions about this. If not, let's look at question number 12 from the homework assignment. So you have a tug of war between two teams, equally strong. Identical rope is tied to a tree, and 10 people, the same 10 people, pull just as hard on the loose end. Which is more likely to break? So you have, in the first case, you have, let's see, so here is the rope, and you have, in the first case, you have 5 people pulling this way, and the other 5 people are pulling this way. They are equally strong, so they are pulling with tension forces that are the same. So this is the first case when there is this tug of war. Now, the second case is this end of the rope is fixed, tied to a tree. It is tied to a tree. And now you have the two teams are pulling the rope with twice the force. In which case it is more likely to break the rope. And look, what happens is that, well, you're pulling this way, but due to the action-reaction law, the tree is pulling with the same force in magnitude in opposite direction. And now you see that the forces here are twice larger than the forces for the first case, and this is why it is more likely to break the rope in the second case. Just the action-reaction law generates a force, and the result is twice larger tension in the rope. Okay, any remarks and questions? If not, let's go to question number 13. Okay, again, elevator question. So elevator is moving upward with constant velocity. the scale inside shows your weight. So the scale, remember, it doesn't matter which way the elevator is moving. What matters is in which direction the acceleration is. Well, in the case of motion with constant velocity, the acceleration is zero. Zero acceleration means that you have zero here, and the result is that the normal force, the apparent weight, is the same as mg, as the normal regular weight of the person. So the correct answer, that's a mistake. So that's okay. So you're moving with constant velocity. Okay. Part A, you're actually, they say that elevator is slowing down as it comes to a stop. Slowing down as it comes to a stop. So it is still moving in whichever direction it does, it doesn't matter. So if it is slowing down, initially his velocity is this velocity, and at next moment of time, his velocity is smaller in magnitude. So acceleration is the rate of change of velocity. Here, what is the change? The change is going to be final minus initial always. So it is going to be this vector minus this vector. Is going to give you a vector that is in this direction. Therefore, the acceleration is going to be in downward direction. In downward direction, well, I erased the diagram, but my downward direction was positive. So this would be what was it? It was positive, right? Downward direction for me. Final minus, it is the other way around. Look, it is final minus initial. So this is negative. So if this is, let's say, 7 meters per second, and this is 5 meters per second, final minus initial means 5 minus 7 is negative 2 meters per second. In other words, the direction of acceleration is not going to be downward, but upward in the coordinate system that I had and I erased. Upward acceleration, negative acceleration. This number would be negative. Negative times minus gives you positive number, and therefore the apparent weight is going to be larger than 675. And this is a mistake.
Well, the question says the elevator is moving up.
Well, in which direction it is moving? Oh. But after that it is saying slows down as it is moving up, but slows down. So the velocities have to be this way. So initially the velocity is V naught is this way, and V final is this way and smaller, like this. So the change of velocity is final minus initial. So it is going to be a velocity change directed this way, and this should be also the acceleration, the direction of the acceleration. That direction is negative in my coordinate system. Negative times negative is still positive, and it is still half. What happens here? Final minus initial. It is actually final minus initial. This minus this is going to give you direction that
Since
is,
the elevator is moving up, the value of acceleration due to gravity is negative. And even if
yeah, the
acceleration
problem is
constant,
that I erased my coordinate system and I'm still trying to use it. So in this coordinate system, what I should get is a positive acceleration for the coordinate system. And I'm not getting it. So delta V as final minus initial should be pointing this way. It should be positive, positive minus with minus sign, so it works. Again, what matters is to have a coordinate system that is well positioned. You have to stick to one coordinate system. So let's see, we had here the floor, we had the object here, and our choice of coordinate system. Our choice of coordinate system was this way, positive. So if this is the positive direction, the acceleration in this case is going to be final minus initial is going to give you acceleration in downward direction. Downward direction is positive. 9.8 minus some positive number gives you a smaller apparent weight. So you see that the things can be quite confusing. You can get intuitive understanding of how the elevator, what would be the apparent weight. So basically, if you're not fighting gravity, you're going to have a smaller apparent weight. And this is for part A. Let's see part B. So look at the explanation here first.
I see what you did, Mr. It was right here. This part, you went according to this coordinate system up to this part. But after this, it should be. And since you are going up, you change the sign to.
No, this look
this.
we have.
And since for the up case,
No, there is a negative sign right here, which I erased, and that negative sign actually inverted. So this is fine.
oh, okay.
This is perfectly fine. I just shouldn't erase problem and try to reproduce it. So it works. It works. Read the answer that they give you. And part B, what would be the reading of the scale when the elevator is stopped? Well, if it is stopped, the acceleration is 0, and you're just going to have normal force equal to mg, which is the 675 that they give. Okay, so we're running. Yes.
I think what's wrong is because velocity is pointing upward, so the lottery's got negative numbers, right? So
Okay.
it'd be negative final velocity minus a rate.
Yeah, that's exactly right. So in this coordinate system, initial velocity, let's say, is -7 meters per second. Final velocity is, let's say, -2 meters per second. And the change of velocity is going to be -2 minus 7 is going to be positive 5 meters per second. Positive for acceleration. Therefore, acceleration is positive. Positive number here gives you exactly. That's again, coordinate systems make the things pay attention for it. And part C of this question, how does the value registered on the same scale compared to 675? When the elevator picks up speed again, picks up its speed on its way down. So on the way down, picking up speed. So you have something like this. On the way down, you have this initial, let's say 3 meters per second, and final, let's say 10 meters per second. So the change, delta V, is final minus initial is 10 minus 3 is equal to 7. So it is positive 7. Acceleration is positive. So 9.8 minus some positive number is going to give you a smaller apparent weight.
Professor,
Again, yeah.
we have a few questions online. asking
Okay,
about the take-home
let's see the first one. Can you read it? I cannot see.
Question about the take-home test. Does he want our answers written in ink or does it matter?
So the question for the take-home midterm, should you write on ink or it doesn't matter? Well, it doesn't matter because you're going to send me eventually a PDF file. So as far as the picture is visible, the PDF file is visible, what was the original writing tool doesn't matter that much. Hopefully, okay, any other questions?
The other questions were very similar.
Okay.
The answers, no.
Okay. Let's, before we finish, we have about 2 more minutes. Let's see how to approach problem number 17. Problem number 17 is about satellites. So they say that you have a satellite that is this distance above the surface. And they're asking what is the acceleration due to gravity there. Right? Off to the surface, the acceleration due to gravity is 9.8. But what is the acceleration due to gravity at that distance, which is substantially above the surface? And the way to answer that is just recall how we derived the acceleration due to gravity. So the gravitational force F, let's say, was the gravitational constant, the mass of the planet Earth, times the mass of the object divided by the radius of the planet Earth squared. Because if you're close to the surface of the planet Earth, the distance between you, the distance between the small mass and the planet is pretty much equal to the radius of the planet. So we call this expression acceleration due to gravity, and numerically it is equal to 9.8. Now, when the same object is at a distance equal to 3.59 times 10 to the 7th above the surface, what happens is that you have the same gravitational constant, the mass of Earth is the same, the mass of the object is the same. However, the distance between the center of the planet and the object becomes the radius of the planet Earth, plus that distance that they give you, 3.57 times 10 to the 7th. Everything has to be squared. Make sure that the radius of the planet Earth is in meters. And this expression is your new acceleration due to gravity, G prime. And you're going to get some acceleration due to gravity smaller than 9.8 because in denominator you have a larger number. So let's stop here. And so after you are done with the midterm, remember the deadline is tonight, midnight. After you're done with the midterm, please work on the homework assignment on chapter 4. And on Monday, we're going to solve any problems from chapter 4, the homework assignment that you asked. be solved. Okay, so see you on Monday.